Hello. Hello.
Yes. You are audible.
सुना है audible तो?
So good afternoon, students. Am I audible, students?
Yes, sir.
Yes, sir. Good afternoon, sir.
Good afternoon, all. No need to wish me. It's all right. Today we are going to discuss about experiment number 6. In the previous class, you have studied about the experiment number 8 probably, isn't it?
Yes.
Yes, sir.
Yes. So today we are going to discuss about experiment number 6 for the relationship between the power system, line voltage and phase voltage of three-phase system when the loads are connected in star or the loads are connected in delta. Before starting the discussion on about the experiment, let me tell you some things so that your lab class will be bit smooth. In the institute campus now, the internet connectivity is having some problem. So sometimes it may happen that you are not able to follow the presentation or the video which I will share in the lab class. So no need to get panicked about it. This is due to the lag or the slowness of the internet connection only. I have already shared the video with you in the Gmail. Also, I will upload the videos in the MS Team group also against the experiment number 6. PPT
Sir.
already, yes.
Sir, I am not added in the EEC01 lab class in MS Team, sir.
Then how have you joined, my dear?
Sir, from the link of on WhatsApp group, sir.
Okay. Then you write an email to Dr. Tushar Kanti Bera sir mentioning your institute email ID. Definitely he will add you in the MS Team group. You should not be worried about it. Okay.
Okay, sir. Thank you, sir.
Okay.
And sir, please upload the video of the previous experiment also. That RLC circuit.
No, RLC circuit, Dr. Biman Kumar Saharoy will upload it. Definitely, I will tell him, I will convey your message to him so that he will be able to upload. He will upload the experiment number 8. Okay, don't worry for it.
We have received 3 videos of experiment 6 through our mail ID. Will you upload the same videos in MS Team?
In MS Team also I will upload them because many times I was not able to share the editing option to you. So maybe you are facing some problem. So I will upload those videos again in the MS Team. But today during the experiment, due to the lack of internet speed, it may happen that your audio is running bit fast, video is running bit slow. Ignore this. You try to understand what I have done during the experiment time. Maybe it will be a bit lag. It may not look good to you at this moment due to slow internet speed, but once you will see it in the video in your own system, that will be clear to you. Moreover, before conducting the experiment, I will discuss some theory related to the experiment, what we are going to perform and all those things. So that even though if you are not able to correlate the audio and video properly, at least just visualizing the video, you will be able to understand what is happening. And based on that, you will I will take the questions from you also.
Sir,
Yes.
sorry to interrupt, sir. Is this meeting for section I also?
I and J only.
Okay. So there are actually two meetings listed in the calendar.
It is clearly written for FGH, that is division A, and for I and J, division B.
Okay, sir. Thank you.
Okay, sir. So,
and one more thing, the video which you have given to us in the Gmail, sir, that is not being played. It is saying that access is denied. You have to.
Yes, you request the access. I am giving the access one by one once it is coming. Okay, to me. I am giving access. Those who have requested earlier, I have given them the access. I am giving now also. Many students are asking for. I am giving the access, and maybe later on also I will give the access. And moreover, I will upload this video in MS Team also. There is no problem at all. Because
yes, please upload it.
Yes, I will upload it in MS Team also. Actually, some other faculty members supposed to take this experiment today. Suddenly, he has faced some problem. That's why I have uploaded the video. It is a bit late in uploading, and that's why these problems have arisen. Okay, so these things are there for today. Now, my dear students, keep your patience. Listen my instructions as well as listen what I am discussing. After that, correspondingly, you ask the question to me at the end of that. Now I am telling you one thing. If during the discussion of the experiment or when I will present the experiment, then that time by chance if you find that I have been logged out, then you definitely, whoever is the seer of your group, you definitely call me. I am just sharing my mobile number so that you can call me and you can notify me, because when I will share my screen, I will not be able to see what is happening in the background, whether I am in logged in condition or logged out condition. So please immediately call me if this type of things happen, because today there is critical condition in the institute internet service. So that's why I am saying all those things to you. Okay. Now, let us start discussing the experiment. I will run the experimental video also, so you should not be worried about it. Okay, so my dear students, I am sharing the screen. You tell me if you are able to see the screen. Can you see the PPT, my dear?
Yes, sir.
No, sir.
No, sir.
No, sir.
No, sir.
No, sir.
No, sir.
No,
No,
sir.
sir. So,
Those you wait bit more, maybe your site
No.
also may have internet connectivity slow, so that's why it is coming bit late. When some people are able to see it, that means it will come. You don't worry.
Yes, sir, now it is visible, sir.
Yes,
Now
you
it's
keep.
visible.
That's why I told you, since the network issues are there today, you keep bit patience. Otherwise, if continuously if you interrupt, then we will not be able to progress properly. So keep bit patience. If this is happening, then correspondingly for a longer time, then definitely we will have to do the things which are needful during the experiment. It is a teamwork. You and me all are within the same group. We will have to conduct this experiment and the discussion related to it together. So can you see the experiment number 6E51, that screen, my dear?
Yes, sir.
Yes, sir.
Yes, sir.
Very good, my dear. I will change the slide very slowly so that even though there will be lag in someone's internet connection, then he or she will be able to see it properly. Myself, Dr. Aniruddha Bhattacharya, today I am going to discuss with you the experiment number 6, that is to study the balanced three-phase system for star and delta connected load. So the star connection looks like in the introductory class of 3rd January, I told you, suppose this is one load, this is another load. Those who are using the mobile phone, just you can touch the screen and you can enlarge your screen. You can zoom your screen, then you will not be able to understand. See this one as very small. You can make it bigger. Suppose three phase. Three phase means there will be 3 lines which will come actually, which are carrying the supply. 3-phase supply. Normally in India we use the nomenclature RYB for 3 phases. If the incoming line, incoming power of R phase will be connected to the load like this, Y phase will be connected like this, and B phase will be connected like this, and their other end will be connected together in a common point. This connection is known as star connection. This is load of R phase, load of Y phase, load of B phase. From the common star point, if I take a wire, that is known as neutral wire. So between any phase to neutral, if we measure the voltage by connecting a voltmeter, this will give me the phase voltage. Phase voltage. Similarly, if I connect a voltmeter between Y phase and neutral, it will give me a phase voltage of Y phase. And similarly, if I connect a voltmeter between the neutral and the B phase, this will give me the phase voltage of B phase. If I want to connect the voltage between any 2-phase wire, that means suppose this is R, this is Y. If I want to measure the voltage between R and Y, then what I will have to do? I will have to I will have to connect a voltmeter between this. So this will measure the voltage between R phase and Y phase, VRY. This voltage VRY is known as line voltage. Line voltage. So we have 3 lines R, Y, B for 3 phases. So between any two lines, R or Y, R and Y, or Y and B, or R and B, if I connect a voltmeter and measure the voltage, that will be the line voltage. Between neutral to any line, if I connect a voltmeter and measure the voltage, then it will be phase voltage. So VRN, VYN, VBN, these are called phase voltage. Now from this diagram, if I will ask you, my dear student, can you tell that in this connection whether the phase voltage and line voltage will be equal or unequal? What will be your answer? Anyone?
Unequal, sir.
Unequal.
Unequal,
That's
sir.
very good. Unequal.
Unequal, sir.
Yes. Very good.
Unequal, sir.
So in this connection, I told you known as star connection. So in the star connection, line voltage is not equal to phase voltage. Very slowly I am covering because internet is slow. If anybody is lagging, so that he can also make it up. Now, which one will be line current and which one will be phase current? If you see the load of each limb of the three-phase connection, these loads are in the three limbs. This is one limb, this is another limb, this is another limb. So the current flowing through this limb is known as phase current. So IR phase, it is the R phase current. For this, it will be IY phase. For this, it will be IB phase. Then which one will be the line current? Current flowing through the line will be the line current. What are the lines? R, Y, B, these are the lines. So if I connect the ammeter in the line, so this will measure the IR line. Similarly, if I connect the ammeter here, this will measure IY line. And if I connect the ammeter here, this will measure IB line. If I connect a ammeter in the limb, inside the limb, any ammeter, this will be your phase current ammeter. So this will measure the phase current. Now, just looking at the diagram, if I will ask you, my dear student, can you tell me whether the line currents will be phase current in the star connection or not? What will be your answer?
Yes, sir.
So,
Yes, sir.
very good. So, in star connection, line current is equal to phase current. Very good, my dear student. Very good. You have understood it properly. So, this is star connection. So, I told you to connect the three-phase load as Y or
Please again
star.
explain that point. Line current is equals to phase current, that point. Once
Yes.
again, please.
Where I am connecting, where I will measure the phase current, I will measure the phase current. That is, I told you these are the three phases. Let me change the color. Okay, my dear student, just allow me to change the color. Okay. So this is the corresponding one limb. This is the another limb. This is the another limb. So in through the current flowing through each limb, these limbs are the corresponding phase current. So if I connect the ammeter in the limb, that will measure the phase current. And what are the lines? This is one line, this is another line, this is another line. If I want to measure line current, I will have to connect the ammeter here. So the current flowing through this line will also means the current flowing through this ammeter, same current will flow through this ammeter also, but this ammeter is measuring phase current, this ammeter is measuring line current. Then if these two currents are same, then definitely I can say in star connection line current is equal to phase current, isn't it?
Yes, sir.
Yes, sir.
Yes, sir.
Now, so Y connection, I think you have understood star connection. Now delta connection, how it will look like, let us see, and what will be the relationship, let us see that one in delta connection.
So what is balance system?
I will tell you, my dear, balance system you will understand bit later on. Let us first understand the connection, then we will go to the system. Okay.
Okay, sir.
Now we have three loads like I showed you previously. One load. Now this is another load, another limb, and this is another load. Three loads are there. Now if I connect the load, suppose this one is equal to R phase load, this is your Y phase load, this is your B phase load. As for example, let us. Now if I connect this terminal of the load with this terminal of the load, if I connect this terminal of load is equal to this terminal, suppose this is A1, A2, then this is B2, B1, and then this is C2, C1. Okay, so if A1 will be terminal of the load of one phase will be connected to B2 terminal of the load of other phase, then B1 terminal of that phase will be connected to C2 terminal of the other phase, and again A2 will be connected to C1. Then this connection is called delta connection. Delta. Where the lines will be there, three phase lines. One line will come like this, will be connected to this vertex. Another will come, it will come here to the another vertex. Suppose this will come and will be connected to another vertex. So R, Y, B. Now line current I will measure, I will connect one ammeter here, one ammeter here, I will connect one ammeter here. To measure the phase current, I have said that you will have to measure the current flowing through this load. So through this load, if I want to measure the current, where I will have to connect the ammeter? For this here, for this I will connect ammeter here, for this I will connect ammeter here. Now this current, suppose these currents are coming like this, after coming to this point, it is getting divided into how many parts? Two parts, isn't it?
Two parts.
Yes, sir.
Similarly, this current is divided into two parts. Similarly, this current is divided into two parts. So, can I tell line current is equal to phase current in delta connection? Not at all.
No, sir.
No, sir.
This
No, sir.
current cannot be equal to these currents individually. Addition of this plus this will be this. But individually, this cannot be equal to this. So, in delta connection, line current is not equal to phase current.
But voltage will be equal.
Yes, my dear, you are absolutely correct. Because if I want to measure the line voltage, this is the voltage between R and Y line. So VRY line voltage between VY and B. This is the line voltage. and between R and B, this will be the line voltage. And phase voltage, if I want to measure, I will have to connect a voltmeter here for the voltage across this load. Then similarly for this, I will connect a voltmeter across this load. I will connect a voltmeter across this load. Now this voltmeter, suppose this voltmeter is connected to this point and this point. Now this point is continuity is there through this square and it is same as this. Similarly, this point continuity is there is same as this point. So between this point and this point, this voltmeter is connected. Also, this voltmeter is connected. But this voltmeter is measuring R phase voltage VR. This is measuring the voltage of Y phase and this is measuring the voltage of B phase. But here you can see this voltage is same as this voltage because they are connected between the same two nodes. So what is the conclusion? As one of your friend has said, line voltage will be equal to phase voltage in case of delta connection.
So in delta there is no neutral point.
No, there is no neutral point. We cannot bring out the neutral in the delta connection. So wherever we require the neutral, we need to connect the loads in star connection, or our supply should be 4-wire supply, 3 for 3 different lines and 1 for the neutral. So that's why later on in the advanced years or semesters of your course, those who belongs to ECE electrical department, they will heard the name 3-phase 3-wire system, and similarly you will heard 3-phase 4-wire system. 4-wire means one neutral wire is there. So just looking at the name, you will be able to understand this is definitely a star connection. But looking at this, you will not be able to say whether it is star and delta, because in the star also, if you don't take any wire from the neutral, then it will be 3-wire system. And in delta, definitely you cannot take the 4th wire. So 3-phase 3-wire can be star, can be delta, but 3-phase 4-wire means always star connection only. This is for ego extra. This is not related to the experiment. So you don't need to take it as a burden, my dear. This is just additional information for you. Now, one of your student was saying, sir, what is balanced system? So delta connection we have understood. Now, one of your friend was asking for the delta connection, sir, a balanced connection. Sir, what is balanced connection? Very good, my dear question. Question is very good. If my loads are equal in magnitude of each phase, whether it is star, whether it is delta, if my loads are equal in magnitude and the amount of voltage supply we are injecting in 3 lines, if they are equal, then we call it balanced supply and balanced load. But if I'm removing this, my dear, I'm removing, you just remember this one relationship. Again, I am removing the drawing, or let me go to some blank slide also. That is also possible later on at the back. Slides. Let me come from the very basic of waveform. Slide has changed. Can you see a blank slide, my dear, now?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes.
Very good, my dear. Very good. Very good. Very good. Very good boy. Very good. Now, if 3-phase supply, you know it is AC supply. So you are aware of the AC waveform, isn't it? In your 10+2 level, this type of waveform you have seen. Many waveforms you have seen. Roughly, I am drawing this one. This side can be omega t, or it may be theta, it may be t. In the x-axis, in the y-axis, we say the magnitude. If it is voltage, then in that case V will be there in this. This is for one phase. Suppose this is for R phase. Then, my dear student, what will be the voltage of Y phase in the balanced connection, balanced supply? The Y phase will start 120° after the initiation of R phase voltage. So R phase started here, Y phase will start after 120°. Sorry, it is not visible. Let me take, actually it should be yellow, RYB, but since it is not taking, let me take black one only. So it will start from here. This is 2 pi by 3, this much distance. Then Y phase will start from here. Maybe it will complete, its magnitude will remain equal. Then maybe it will be like this. Maybe it will complete its supply like this. Then it is like this. Maybe it will be like, sorry, I'm not person who can draw the things very good. Just roughly I can draw it like this. Here, if the peak value of this wave and this voltage will become same, and if they are 120° apart, then you can say that R and Y phase both are balanced with respect to each other. Now, three phase, I have another phase, my dear. So B phase is there. So B phase will start its operation 120° apart. So this will be like this. Maybe it is starting like this. Maybe it is starting like this. So it will be like this. It is starting 0 here. It started here. So it is from here to here another 2 pi by 3 with respect to Y, and the B phase is starting its operation. If the magnitude of B phase supply will be also same as your R and Y phase supply peak value, and correspondingly in that case, then maybe it will look like this. It will go on. Here R, Y, B, if their peak values are equal in magnitude and each of the phase is 2 pi by 3, that means 120° apart from each other, then we can say balanced supply. Voltage, if it is a voltage. Now, my dear student, you have studied RL load, RC load, RL circuit, RLC circuit, RC circuit in the previous experiment. From that experiment, at least you have understood that if in a circuit, inductor will be there, capacitor will be there, then current will lag or lead respectively with respect to the supply voltage. That means if the R phase voltage has started here, its current may start after certain angle, after certain time. Maybe it is starting here. Maybe it is starting, depending upon the phase lag the current is having if an inductive load is connected. If the capacitive load will be connected, then you will find current will be ahead of the voltage. Then in that case, the waveform may looks like this for the current. Anyway, I'm not talking about the current. But if my loads are resistive in nature, then definitely there will be no phase lag between the voltage and current. That means if the voltage is starting from here, current will also start from here. If the voltage will be 0 here, current will also become 0 here. Like this maybe for R phase, then similar for yellow, similar for blue, and all phases, R, Y, B, all phases. So in our experiment, if the loads are, I am coming back to my diagram, my dear. Can you see that red diagram of delta connection again?
Yes, sir.
Yes,
Okay, very
sir.
good.
Yes, sir.
So,
Yes, sir.
okay, my dear.
Yes,
Very
sir.
good. So these loads are equal in magnitude, I told you, if it is balanced. So if voltage are equal, load magnitude is equal, then current is equal to, current phasor is equal to voltage phasor by impedance phasor. If impedance phasor is same, voltage phasor is same, then current phasor magnitude will also be same for each phase. Then the currents are also balanced in that three-phase circuit where the three-phase loads are also balanced. So in order to make current balanced, our supply should be, three-phase supply should be balanced. That means each phase voltage will be 120° apart from each other, and they should have equal magnitude. And similarly, the loads connected in different phase limbs should be equal in magnitude. Then the currents will also be balanced. Current magnitudes will also be balanced.
Sir, I cannot understand why in the balanced condition the phase angle difference will be 120°. Can you please explain it again?
Yes, at this moment you will not be able to understand, my dear student, but I can tell you the machines which produce the three-phase supply, that is synchronous machine, if that three-phase power voltage waveform can be generated using the machine construction, machine windings are like that, that the voltage waveform which will be produced by that will be 120° apart from each other. Then only it will be able to cover 360° periphery. If they will be, suppose, in the same phase, then what will happen? In the other side, you are having 360° difference between this. Between this 0°, between this side, it is 360°. That also is possible in some specific case, but you will have to make it forcefully like that to make the phase shifting 0. But that condition, we don't call it balanced. You are not in that position at this moment, so that I will be able to explain you and you will be able to understand it at this stage. Once you will be in higher semester, if you belongs to electrical, you will understand it automatically when you study it. But still, if you are not studying it, if you are in the mechanical, you have the electrical machines in the 4th semester. So mechanical students will also be able to understand it. Okay. At this moment, it is not possible for you to understand it. How is it possible? Because it will be too difficult for you that many students will not be able to understand it at this moment. Because we will have to go for the geometry of the machines, then how the machine work and all those things. Because all these things, voltage currents are produced, means it's an electromagnetic circuits due to electromagnetic induction and other things, the variable MMF distribution, then the based on the Faraday's laws of electromagnetic induction, EMF induction, these are happening. So how these conditions are produced in different machines in a different way, and accordingly we get the supply.
Okay, sir.
Now, if in the last class you are aware about the phasor diagram. So in the phasor diagram, if we draw the three-phase phasor diagram, then I told you three-phase voltages are 120° with respect to each other. If I consider R phase as reference, then the yellow phase voltage will be 120° lagging with respect to the R phase voltage. So it will be VYN. And B phase voltage will again be B phase voltage will again lag the Y phase voltage by 90°. So VBN. So if this is 120°, this is 120°, automatically this will be 120°. Now, if I come here, in delta connection, line voltage is phase voltage. So in the delta connection, the VRN is same as VRY, is same as VYB, is same as VBR. So in the delta connection, what we do is that we draw the phasor diagram of VRN like this. Then we draw the phasor diagram of V. Let me take it here. V, suppose V in the same phase it will be. If its direction is same, so VRN, VYN is in this direction. I will take it like this, and this is VYN, and VBN is this. This is the direction. Actually, I could not draw it properly. This line and this line should be parallel. This line and this line should be parallel, and this line should be parallel. So in that case, if it is R phase tip, this is Y phase tip, then definitely this is VRY. This is tip of Y phase. So this is tip of R phase, between R phase tip and Y phase tip, VRY. Similarly, this is R phase tip, this is B phase tip, then this is equal to VRB, and this is B phase tip, this is Y phase tip, this will be VYB. So you can see in delta connection, VRY, VYB, and VBR, RY, YB, and BR, all are same as RN, YN, and BN. So what we can write under balanced condition, VRY is equal to VYB is equal to VBR is equal to VRN is equal to VYN, VBN. One thing is that magnitude should be equal for each phasor, as well as each phasor should be 120 degree apart from each other. Then only we call it, it's a balanced. Magnitude and the phase angle difference with respect to each other should be equal. So here I should give the symbol of them are equal. Magnitude symbol I should provide. Angle is 120 degree apart, definitely I should not say like that. In case of star connection, then what will happen, my dear? In star connection, let me see what will happen. I told you VRN is this one, VYN is this one, and VBN is this one. This is 120 degree, this is 120 degree, this is 120 degree, 120, 120, 120. Now, if I will ask you in the star connection, what is VRY? Star connection, how it was looking like? This was looking like a star connection. So this was your R, this was your Y, this was your B, and this is neutral. So if I will ask what is VRY, what will be your answer? Sir, it will be VRN plus KVL. You are applying simply KVL. VNY. I will say yes. VRY will be phasor, will be VRN phasor plus VNY phasor. NY means VNY means minus of VYN. So what I will do, if I want to calculate VRY, I will take a phasor of equal magnitude of YN in the opposite direction. Then this will be my VYN. Then the resultant of these two, my dear student, resultant of these two, will be my VRY. Then you will ask me that what is the relationship, sir, between VRY and VRN or YN? I will tell. Let us see, my dear. VRY magnitude will be magnitude of square root of parallelogram rules. VRN square plus minus VYN square plus magnitude of VRN into magnitude of VNY or minus VYN into cos of their internal angle. Internal angle, how much is the internal angle, my dear? Can anybody tell me what will be the internal?
120.
Hey, not 120. You see?
60.
60 degrees.
60 degree.
60
Very
degree.
good. This much is 120 degree. This is 60 degree. How? This is 120 degree. That means this is 180 degree. Full is 180. If this much is 120 degree, that means this is 60 degree. Again, this is 120 degree. This is 60 degree. Then this much will be 60 degree. Then cos of 60 degree. Then what will happen, my dear? We know V balanced supply, I told. So VRN magnitude is equal to VYN magnitude. Then I can write any one of them instead of this. Then I can write 1 square plus 1 square plus 2 into 1 into 1 into half. Then this will be within the, and I can bring VRN outside. Or VYN also we could bring outside. There would not be any problem. Then this is coming equal to root 3 of VRN. Okay. So this is phase voltage. This is line voltage. Then what is the relationship between line voltage and phase voltage in star connection? The relationship is equal to line voltage is equal to root 3 type of the phase voltage magnitude in terms of magnitude. Is it okay, my dear?
Yes, sir.
Yes, sir.
There will be
Yes.
minus.
No minus. This is magnitude only, isn't it, my dear?
Okay, sir.
We are talking about magnitude. So,
Sir, how VRN is equal to VYN in
because
magnitude?
we have considered the balanced supply, that this phasor magnitude length, this phasor length, this phasor lengths are equal, balanced supply, isn't it?
Oh, sir, I understood.
Okay. Now, the thing is that, so I told you line voltage and phase voltage are equal in delta, it's fine. But for star, line voltage is equal to root 3 of phase voltage. In delta, line current is not equal to phasor current, but in star, line current is equal to phase current. Similar phasor diagram, if we draw for the current and do the calculation, I am not doing this one, then what you will find that in star connection, in delta connection, you will find I line current is equal to root 3 of I phase current. Just similar to the star connection voltage relationship and delta connection current relationship are same. But if it will be balanced, if it will be unbalanced, some different relationship will come. Drawing the phasor diagram, their length and other things, and using geometry, you will have to find out the relationship in that particular condition for which these are unbalanced, depending upon their unbalanced nature.
Sir, one doubt. Sir,
Yes,
in the phase voltage in the this one star connection, sir, we have found out geometrically that the angle will be 60° according to the phasor which we have drawn. But sir, in the which you are talking now about the line current in the delta connection, sir, how can we say that it will be 60° angle, the resultant of the two vectors?
Yes,
Can
my
you
dear,
come to-
what I told, if my loads are resistive in nature, I told you, isn't it? Then the phase angle difference between the voltage and current is 0, isn't it, my dear? Then in this diagram, if this much voltage you are injecting, that much voltage you are injecting means this much VRN voltage you are injecting. If the resistive loads will be resistive, then there will be no phase difference between voltage and current. Then where the current phasor will lie? The current phasor will lie also in the same phase as the voltage phasor if the load is resistive. Similarly for Y phase, this will also lie in the same phase, and for the B phase, this will also lie in the same phase, provided if the loads are resistive in nature. Number one. Number two, the magnitude of the load should be equal. Current is equal to voltage by impedance. If voltage magnitudes will be equal, impedance magnitude will be equal, then the current magnitudes will be equal. Then this tip length, this length will be equal to this much tip length. This will be equal to this much tip length. Done? Then you will ask me, then
sir.
in case of inductive capacitive, what will happen? I will tell, my dear, same will happen, but in a different way. Then you will ask me, what is the difference, sir? I will tell, listen, my dear. Suppose I have a, let me go back, go at the end where I will get some blank page. Let us consider we have a RL load. Instead of R, we are having a RL load in a particular phase, suppose VRN, RL. Then what will be the current? Current phasor will be voltage phasor divided by impedance phasor. Then what will happen? VRN phasor is equal to its magnitude in angle. Then what will happen? What is the magnitude of impedance? It will be R square plus omega square L square. In the last class you have seen that one. And what will be the angle? Angle will be tan inverse omega L by R. Suppose let me take theta. Now, if my VRN will be equal to VYN will be equal to VBN, then this magnitude is same for the R phase current. Similarly, when calculating for Y phase current, this voltage magnitude will remain same. For the B phase also, this will remain same. Now, in each phase, the value of resistance and inductance, if will be equal for all phases, then this magnitude will also be equal. This angle theta will also be equal. So, in that case, if this is for R phase, this is for Y phase voltage, and this is for B phase voltage. Since, just a minute, let me take some different color. Since current is lagging by angle theta degree, suppose this is R phase current, IR, this is angle theta. If R and L will be same for all phase, then this theta will be also same. The lagging angle for current will be same as for other phase. This will be also theta, and similarly this will also be theta. Then ultimately, if this is 120°, then this is 120° plus theta, but you have come here theta, then what will be the angle between this? Also 120°. This will also be 120°. This will also be 120°. Ultimately, even though currents are shifted from the voltage, but their internal angle is 120 degree apart from each other and their magnitudes are equal, then geometrically, if you want to find out the resultant, ultimately the same √3 relationship will come, isn't it?
Yes, sir.
Then
Yes, sir.
allow me to go to the experiment. I have discussed the theory that these are the relationship. Now, what is your job of your experiment? To establish this relationship. Really, in case of delta, line current is equal to √3 of phase current. In case of star, line voltage is √3 times of phase voltage or not. That is the only thing you will have to measure. That's all. So let me see. Oh, let me come to my experiment. Already spent lots of time. Let us try to do it bit quick. Now, line voltage is this one. The voltage between any two lines of three phase. These are already I have said you. And line voltage, phase voltage relationship also I have told you. For three phase, the power is equal to 3 into volt. Because single phase, you know, the power is equal to phase voltage into current into their internal angle between voltage and current. This is power factor. I think in the experiment 8 you have understood. This is for one phase, but we have three phases. So it will be 3 into V phase into I phase into cos phi will be the total power in case of a three phase. Now in terms of line, if I want to represent, if it is star, what will happen? In star, voltage, phase voltage is equal to line voltage by √3 and line current is and phase currents are equal. So I can write I phase equal to I line. So it will be √3 V line into I line into cos phi. In case of delta, what is happening? 3 V phase is equal to V line, but I phase current in delta is equal to I line by √3 into cos phi. So same √3 VL into IL cos phi. Oh, sorry, my dear. Please excuse me. So that's why it is a common formula in terms of line voltage in a three-phase circuit. If I want to represent the power, then √3 VL IL cos phi. In terms of phase, if I want to represent the power, then 3 into B phase, I phase into cos phi. Done, my dear. Let me go to the next slide. What are the equipments are required? I require to measure the voltage current. So I require ammeter. I require voltmeter. Voltmeter, how many voltmeters are required? One voltmeter for measuring the line voltage, one for measuring phase voltage. So 2 voltmeter. Ammeter, one for line current measurement and 2 for phase current measurement, because line currents are getting divided into 2 parts in 2 phases. So 2 phase voltmeters I require. Then since it is a 3-phase circuits, so I require to measure the power, I require wattmeter. You have heard about the wattmeter in the last experiment. So since it is a 3-phase circuit, instead of single phase wattmeter, I will use a 3-phase wattmeter. Then 3-phase supply is there. Previously you have heard about single phase variac. Here 3-phase variac will be there. Rheostat, I am using a resistive load, not inductive, not capacitive, pure resistive, so that the voltage and current phase lag will be 0 degree. And connecting wires as per requirement. What is the connection for my star connection? Let me take the ink. So you see, this voltmeter is measuring, this is R, this is Y, it is measuring line voltage, V line. This voltmeter is across the limb, so it is measuring the phase voltage. This ammeter is measuring connected in the line, it is measuring line current. This ammeter is connecting in the limb, so it is measuring phase current. This ammeter is connected in link, this is connected, measuring phase currents. So what is the connection pattern? If I have 3 loads, A2, A1, if I have another load, C2, C1, and if I have another load, B2, B1, then A1, C1 and B1 will be sorted with each other. And the three supplies will be connected to A2, B2 and C2. That's all. Here, three-phase wattmeter is connected. In three-phase wattmeter, it is like single-phase wattmeter. So M supply will come to M. From the load terminal, the current supply will go to the load. But here, instead of from M and common are sorted, M and V are sorted here. Normally, in single phase, just a minute, my dear student. I'm again sharing it. Okay. Can you see the apparatus required list, my dear?
Yes, sir.
Students?
Yes, sir.
Yes, sir.
So, my dear student, just a minute. So, if normally in single phase, what we find M, L, then we have C and V in single phase wattmeter. Here M is sorted in C, but actually C and V are the two terminals of the same coil. This is C side, this is V side. In three phase, what we do is that M and L as usual, we just interchange the terminal. This is V, this is C. So M and V are sorted. Common is connected to the other phase. So that is the difference. There is no technical difference, only the connection difference. So M and V are sorted. Here also M and V for other phase is sorted. Common, both the commons are internally sorted with each other, and that common point is connected to other phase Y. It is 2 wattmeter, like 2 wattmeter method. Later on in the third semester, those who are studying electrical engineering, they will study this one in the measurement subject, electrical measurement subject. So this connection we will have to make. There is no difficulty. This is star, and in delta I have already explained you. We have two terminals, A2, A1. We have, this will be C1, C2. This is C1, C2, and this is B1, B2. Sorry, this is B1, B2. So A1 is connected to B2, B1 is connected to C2, and C1 is connected to A2. Now this voltmeter is measuring the phase voltage across the limb. This is connected across the line, so it is measuring the line voltage. This is connected to the limb, so it is measuring the phase current. This is also measuring the phase current, and this is measuring the line current. So in our case, experimental setup, what will happen? This is our experimental setup, the panel. So we have three ammeters. This is one ammeter, this is another ammeter, this is another ammeter. Okay, so A3, this is measuring A3, this is measuring A2, this is measuring A1. What is A3, A2, A1? This is actually A3 line ammeter, and A2 and A1 are the phase ammeters. So in this panel, A1 and A2 ammeters we will use as phase ammeters. A3 ammeter we will use as line ammeters. This is the three rheostats, three resistive loads used for three phases. Their terminals are taken here. Their terminals are taken here. This is A1, A2. Similarly, this terminal is taken here internally. So B1, B2. And similarly, these terminals are taken here, C1 and C2, internally. So I do not require to make any connection over here in the rheostat. In the panel, I have two terminal A1, A2, B1, B2, and C1, C2. That's all. From there, A1 will be connected to B2, B1 will be connected to C2 or not. According to the diagram, we will simply make the connections. This is the three-phase variac, looks like. Here in single phase variac, we have the supply like this, and there is the variable point. This is the output. and this is the input. As I will rotate the potentiometer, this pointer will move up or move down. Accordingly, voltage in the output will change. Here, same thing we are doing in the 3 different phases. 3-phase wattmeter looks like this. So you can find these are the terminals of the wattmeter. M is there, voltage terminals are there, common terminals are there. This is for extending the current ranges. B1, B2, E1, E2 terminals are there. I will explain when you will see the video. And here the M and L terminals are there. M and L terminals are there. Then this is the rheostat. In the rheostat, we have 2 terminals. If we connect the meters, if I connect the wires between these two, so whole resistance of the winding will come into the picture. Even though if I will move the jockey, resistance will not change. So this is the fixed resistance connection. But if I make the connection between this to this, then what will happen? The connection will come like this, then through this it will return back. So depending upon the jockey position, how much resistance of the wire is considered, that is being decided. So in between this, if I connect and move the jockey, then it will use as a variable resistance. This is our connecting wires. This is the ammeters. This is our voltmeter. I'm not explaining. We will come to the experimental results later on after seeing the videos. So my dear students, now I will come and I will share the video. Yes, my dear.
Sir, can you repeat the wattmeter again? I can't understand it.
Okay, my dear, definitely. Which portion is not clear? You tell me in the connection of the wattmeter?
Yes, sir, the connection.
Okay. You tell me in your previous experiment, experiment 8, was there any connection of wattmeter? Requirement of wattmeter was there?
Yes, sir, it was there, but it was single phase only.
Okay, no problem. Single phase only. It was there, isn't it? How was the connection? I am drawing it again. You can remember the connection was, and this was connected like this across the supply. This was C, this was B, isn't it?
Yes, sir.
Yes.
Sir.
Here, same we are doing. This is one coil. What is the name of this coil? Pressure coil. What is the name of this coil? Current coil. In the pressure coil, what are the terminals? C and V. In this wattmeter also we are doing the same connections. But what we are doing now? I am changing the terminal points. What I am doing? If these are M, this is L, I am taking V in this side and C is in this side. Then from C I am connecting to the other phase. Then M and V I am sorting. Looking like same. Through the inductor, through the coil where the current is flowing in this direction, that will not create much impact. Definitely in the deflection and other things it will create an impact, but other than this it will not. So here you see M and V are sorted. Common. Similarly, let me take a blank one, page. Let me erase the whole screen. Okay, let me. If 3-phase supplies are there, so in what I will do, this is M, this is L, this is V, this is C, this is connected like this. In the other phase, I will make a connection like this, M, L, then V, C. These two C's are sorted and this is sorted. This is the connection we have made. This is called 2 watt meter method power measurement. In a single watt meter, you measure the power of one phase supply, single phase supply. So automatically for 3 phase supply, you will say we require 3 single phase watt meter. Yes, using 3 watt meter also 3 phase power measurement is possible. But with certain changes in the connection, it is also possible using 2 watt meter method, the 3 phase power measurement. How it is possible? In the higher semester, the derivations, calculation, explanations are there. So it is 2 watt meter method connections. 2 watt meter is connected like this. Only Y phase will be common point is connected to it. So these connections only we have made. You see in our connection diagram, R phase supply is coming, line is going from here. So in between we have the current coil internally, then common and V we have the voltage coil, pressure coil internally. So you see V and M are sorted. Common is connected to the Y phase. Then internally this common and these commons are sorted. Then you see V of B phase is connected to M. M B phase supply is coming. Then we have the current coil here, we have the pressure coil here. That's all, 2 watt meter method. These are internal, so windings are not being shown. Whatever is there inside the dotted portion, that is inside the meter. So this is not shown, only the connections, external connections are shown. Is it clear now?
Yes, sir, it is cleared.
Okay.
Sir, here in the line supply, sir, why we are not using 3 volt meters? Why only 1 volt meter?
Because we are assuming our supply is a balanced supply. So for all the lines, we are assuming the voltage will remain same. You can do it. Whatever you are saying, you can do it. No problem at all. Okay? You can do it. If you are having any doubt that no, my supply may not be balanced, okay, you can do it. You have every authority to do it. So may I go to the experiment video now, because already we are lagging.
Yes, sir. Yes, sir.
During video play, definitely voice and video lag will be there. So please excuse me for this. You please see it once more when you will be in your room using your laptop or mobile. You later on, after downloading that, you please see it once more. Before going to experiment 6, I will show you how our basic electrical engineering or electrical technology lab looks like. So just, I am not running it. Once the video screen is visible to you, then I will play. Can you see the video screen? If
No,
not,
sir.
then I will wait.
No, sir, we can only see
No,
the
sir.
slide.
Okay,
Yes, sir.
let us
Yes, sir.
wait.
Now it
Yes,
is.
sir, now it's visible.
Okay.
No, sir.
Then,
Yes, sir.
okay, let me wait a bit more. No problem. Let me wait a bit more. It is not playing. I am not running it. I have kept it in pause condition. Once it will appear in the screen, then I will run it. It's visible now, my dear.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
This is
Yes, sir.
electrical technology lab, on network lab is also there, electrical measurement. So 3 labs are there inside this building. Actually, some maintenance work is going on. That's why this extra, the bamboos and other things are there. This is the entrance point. So sound is very poor, slow, actually very less. We will enter inside the lab. You just see that one. Lab in which you supposed to perform the experiment physically, but due to the COVID condition, unfortunately we are not able to do it here. This is the entrance of our electrical technology lab. Then this is the way someone enter in the lab. Then if we come inside the lab, this is the table. This is the table where the instructors, that means we used to sit and you used to perform in these tables, actually different experiment, 8 experiments. For each experiment, 2 setups are there. So 16 setups are there for 8 experiment. We used to correct the copy and all those things after sitting here. In which normally the faculty members or the supervisors who are taking care of your experiments used to sit. Every day you're supposed to submit your lab copy over there, previous day lab courses. And after that, in this lab, this portion, you see there are certain almiras in between. The left side portion of the almira is your electrical technology lab. Right side portion of your almira is your electrical measurement lab and network lab. Third semester it is acting as a measurement lab. In the fourth semester it is acting as a network lab for the students of electrical engineering. But our lab, electrical technology lab, is in the left side. You can see so many almiras are there here. In the right side of this almira is the electrical measurement lab is there, network theory lab is there, and the left side portion is your electrical technology lab. You can see lots of setups are there, panels are there, you can see here. And these panels represents the corresponding. Our experimental setup is this one. This last one, right side, this one where my cursor is moving, this is our setup in which we are going to perform our experiment. Your experiment number 8 RLC circuit, this was the panel in which you have performed experiment number 8 virtually. Your experimental setup for all the experiments which is supposed to perform in this lab. So let us come in this side. Different lab setup you can see are available here. Now, since today we are going to discuss. So this was related to experiment number 4. I am stopping it. Just I have given you a glimpse of idea about our experiments. So let me go to our first. So good afternoon. Once the screen will be visible to you, maybe a hazy screen, then you tell me, then I will play the video.
It is visible now.
Visible.
Sir, it is visible.
Yes, sir, it is visible.
Okay, then I'm playing. First, we will do it for the star connection experiment, then we will do it for the delta connection. Please listen carefully. At the end, whatever doubts will be there, you please tell me. Today we are going to discuss about the experiment number 6. As you can see here, the title of the experiment is to study the balanced three-phase system for star and delta connected load. So in the previous theoretical discussion which we have made on 3rd January 2022, we said what is three-phase load, and three-phase loads can be connected in star or delta. That we have discussed. Now here this Y is representing the star connection, this delta is representing the delta connection. So we will have to take a three-phase load. In that we will have to give a three-phase supply. Three-phase supply means in the theoretical class I have said you it will have 3 phases and the voltage of each phase will be 120-degree electrical apart from each other. So if we normal convention which we use in India is the R, Y and B. So R phase, if we take as reference, its magnitude of voltage if it is VR angle 0 degree, then the Y phase voltage will lag by 120 degree with respect to R phase. So Vy will be, phasor will be Vy magnitude angle minus 120 degree. Minus 120 degree, why? Because it is lagging the R phase by voltage by 120 degree. And B phase similarly will lag 240 degree with respect to R phase. So it will be VB minus magnitude angle will be minus 240 degree. So if we come to the circuit diagram, we will have to find out the relationship between the phase voltage and the line voltage, phase current and line current in two different connection, that is star connection and delta connection. So what should be the relationship? In star connection, line voltage should be √3 times of the phase voltage, and line current and phase current should be equal. In delta, line voltage and phase voltage should be equal, but line current should be √3 times of the phase current. How? So this is the star connection load. Here we are using a resistive load in this case. So this is one phase A2 to A1, then another phase is B2 to B1 and C2 to C1. Here three inputs of supply: R phase supply, Y phase supply and B phase supply. Here this is the three phase wattmeter. In single phase wattmeter we are aware of the names M, L, on and V. Here also M, L, C, V is there for one phase. For other phase also similarly M, L common and V. So M1 and L1 we know main terminal, line terminal, common is common terminal and V is the voltage. Here also for other M, L main is the main terminal. You see the supply is coming from main here. Then M is sorted to V and from L the current here also from M it is entering, M and V are sorted, and from L it is going to the load. Both the common are internally sorted. During experiment we do not require to sort them. It is internally sorted, but any one of the common terminals should be connected to the Y phase. That means both the common terminal we can say indirectly is connected. Now this is the three phase system inputs into the loads, three wires. So the voltage between the two lines of two different phase is the voltage. So here this is one phase, its input is this way. This is another phase, its input between the voltage is the line voltage. And the corresponding current flowing through this line will be the line current. And this is phase. So if we want to measure the phase voltage, we will have to connect a voltmeter between any phase terminal of the phase. Either we can connect it between A to A1 or B to B1 or C to C1, anything. To measure the phase current through the phase resistance, how much current is flowing, that we are measuring. We are measuring this current two phases, for B phase and R phase. A1 is ammeter that is measuring the current of B phase, and A2 is the ammeter which is measuring the current of A phase, and A3 is the ammeter which is measuring the line current. So if we want to find out the relationship between line current and phase current, we will have to find out the ratio between the A3 ammeter reading by and A1 or A2 ammeter reading. Similarly, if we want to establish the relationship between the line voltage and phase voltage, in that case, we will have to find out the ratio of this voltmeter reading divided by this voltmeter reading. Here we require 1, 2, 3 ammeters phase wattmeter. And here variable AC supply is there. For that we require a phase variac because it is a three phase supply. Same circuit we will have to make for the delta connected load also. Connection of wattmeter is same. Between the line, if we see this is one phase, this is another phase, this is another phase. If we want to find out the line voltage, input line of one phase, another input line between R and Y, we are connecting a voltmeter. So it is measuring the load voltage, line voltage across any phase. Suppose B phase, we are measuring here B1 and I am dragging it bit because we have discussed those things already. So I will come to the experimental stage directly. Okay, let me set the line voltage. So once the screen will be visible observation table to you, then again I will play the video. Is the observation table Visible to you?
Yes, sir.
Yes, sir.
So
Visible.
it's reverse.
Yes, sir.
Phase current? Yes, we will find you power factor, how to calculate that I will discuss later on. Wattmeter reading, using this wattmeter connection, we will get the wattmeter reading. So this active power of wattmeter reading, that we will be able to get it. Then we will calculate the power also using the three-phase power for calculation formula as well. Here for three different value of, here you can see the load which is maintained. Here one arrow symbol is given, so it is representing a variable resistance. So our load of three different phases are variable loads. So what we are doing, we will vary the load to different value, 100% load connected, 50% load connected, 10%. We can set any different value also, 90%, 45%, 20%, anything. For three different values of load, we will have to find out this ratio and we will have to check the corresponding reading, and all those values we will have to see. So let us see our panel. Before going to the panel, how the three-phase variac looks like, let us see that one. You see, this is the three-phase variac. It's a big one. Here, this is the terminal through which we are varying the voltage. So it is connected at this moment at 0 point. If we want to increase the voltage, we will rotate it like this. So you see, we are increasing the voltage. Again, if we want to make it 0, here it will be automatically stopped. You see, I am trying to rotate it, it is not. This is the internal circuit diagram of this three-phase variac. And from the, since it is a three-phase variac, you can see three wires are coming out of it for three different phases. That's all. Now, this input supply we are giving to whom? To the R terminal, Y terminal, and B terminal. So in the panel, we are bringing the supply, three-phase supply through this variac. So the panel, now in this panel, now in these three terminals, we will get three-phase voltage. Now, if we see this one in the panel itself, all the three ammeters are there. We do not require to connect any external ammeter in this. Three ammeters, you see it is written, this is measuring AY, this is A2, this is measuring A1, this is the ammeter A3. So as per circuit diagram, you please check it, the circuit diagram which you are having in the manual. So you will be able to understand which ammeter is measuring which thing. This is A3, this is A2, and this is A1 ammeter. We require 2 voltmeter. This is 1 voltmeter, externally connected voltmeter. This is another externally connected voltmeter. So this voltmeter is having 2 scales. One is 150 volt scale, another is 300 volt scale. Here in the scale also you can see 3 ranges of the 0 to 150, 0 to 300. If I connect the wire at the between common and 300, so we will follow the upper scale. If I connect that wire between 0 to 150, I will use the lower scale. Similarly, for this one also, it is also having 2 ranges, 150 and 300. Since we are dealing with 3-phase supply, so if we see for in India, normally in LT level, 3-phase supply voltage, line to line voltage is normally 400 volt and above. Phase voltage, LT means low tension. Low tension, high tension, these are the common term used in the electrical power system. Low tension voltage range means 230 volt, 415 volt, 1.1 kV, these are 3.3 kV, these are LT, then 6.6, 11 kV, 33 kV, 66 kV, these voltage ranges are HT, then extra high voltage EHV, HB, all those things terms comes actually around 220 volt and above. So since 220 is greater than, even if it is a phase voltage, so since it is greater than 150, so we are preferring for safety side to connect it at 300 volt terminal during our experiment. We could connect anywhere also, but here we are not. But you may ask me, sir, your reading is less than 150, then why have you not connected to 150? Okay, maybe I am keeping the input voltage lower, but maximum we can increase up to that voltage. So that's why we are keeping it at the connecting it at 300 volts. This is our 3-phase wattmeter. You can see the scale is 0 to 1200 watt, but when for normal condition, this wattmeter, if you see the voltage scale, there are two voltage scale, 300 and 600 for both the phases. Here also you can see 300 and 600. Current, here if two ranges are there, here you see 2.5, it is written 2.5 and 5 ampere. When it will be 2.5, when B1 and B2 will be shorted, it will be lower range, and if B1 will be connected to E2 and B2 will be connected to E1, through this you can see we can change the position like this shunt, and correspondingly we can make the connection like this. Just a minute. You see, if I connect it like this, then the current range will increase to 5 ampere. But we will not increase the current range much in this case for safety purpose. We could increase, but I am not increasing at this moment. You don't think that it cannot be increased for this panel. It can be increased, but I am not increasing it at this moment. So just a minute. Yes. You see, I'm sorting it. So lower range of current will be there, 2.5. So voltage is at 600 volt, voltage scale, current scale is 2.5 ampere. So what will be the multiplying factor? You see, current is 2.5, voltage is 600, it is showing 2 multiplying factor. If it would be 5 ampere, 600, multiplying factor would be 4. So multiplying factor is 2, means whatever reading it will show, we will just multiply it by 2. That will be the exact power consumption of this circuit. This is the 3 rheostat which is representing the 3-phase load. This is 1-phase load, this is another phase load. The wire of these loads are internally connected and coming to this terminal A1, A2, B1, B2 and C1, C2. So instead of connecting the terminals here, I will connect the terminals assuming these are the terminal A1, A2, B1, B2, C1. So I have made the connection according to this. As for example, if we see the wattmeter connection, what we need to do, M should be sorted with V, supply should come to M. Let us see from R phase, you see, from the R phase I have taken it, it is connected to M. M and V will be sorted, M and 600 volt is sorted. From L, it is going to load, that means A2 terminal. It is going to load. You see, this is yellow wire. Okay. Similarly, for this also, M2 and V2 should be sorted. You see, this is our M. So and V are sorted. From L, it is automatic ফেরত হয়ে যাবে। কিন্তু তাহলে আমাকে বলছে ওটা আপনি বাদ দিয়ে ডিজিটাল, বিকজ ইউ সি না, তাহলে অন্য কিছু হয়ে গেলে বিপদ, তো তার থেকে 3 টায়ারে যাওয়া ভালো। উল্টো পাল্টা কোচে ধরুন একজন হয়ে গেলে এই কোচ একজন আরেক কোচের দরকার নেই। L, it is coming to 1 ammeter A1. From A1 it is কি করে বুঝবো? You see, বোঝা কি ওটা বোঝাই যাচ্ছে যে ওই কোচে নেই, থাকলে তো সেম কোচে হলে তো চলেই আসতো।
Which phase load it will go? কেটেছি সেই ট্রেনটা রাত্রে একটার সময়, সেটা সরাসরি ফালাকাটা যাবে না, সেটা ওই ধরুন হাফ অ্যান আওয়ার 40 মিনিটের জন্য নিয়ে আর কি কাছাকাছি আরেকটা স্টেশনে।
And
তাহলে ইয়েতে দেখতে হবে
your
তৎকালে, কিন্তু তৎকালে দেখলে তখন এই 48 ঘন্টার মধ্যে ঢুকে যাবে, বেশি টাকা কেটে নেবে।
connected. So let us see. This is
আমি
ammeter.
আসছি তো
It will be ammeter from A phase.
চলছে
From R it will go to A1, it will go to A.
যাই না, একটু দেখুন তাহলে।
L it is going to
যা বাবা, আমি তো দেখতে পাচ্ছি না।
it will go to one ammeter. Common terminal of A phase, B phase. Common terminal of A phase, B phase, C phase means A1, B1 and C1. Here is
ইনস্টিটিউট মেল
B1
দিদি
and C1 are sorted.
তা তো করতে পারছেন
A1
না।
is sorted via ammeter connected to B1 via ammeter. So this is the connection and voltmeter. This is the corresponding line.
না ঢুকতে পারো তো কিছু না, ঢুকতে পারাই উচিত তো, তাই না?
Connected, you see this between R and Y, measure is line voltage, and phase voltage should be measured by this voltmeter. It should be connected.
জানি এই ভিডিওটা শেষ হলে একবার দেখবো স্ক্রিনে কিছু দেখা যাচ্ছে কিনা।
আমি তো রাজদীপের ঢুকে ঢুকলাম যে আমি শুনতে পাচ্ছি না, আওয়াজ শুনতে পাচ্ছি না।
You see this red wire
শুনতে পাচ্ছেন
আওয়াজ শুনতে পাচ্ছি
and
কিন্তু দেখতে পাচ্ছেন না কিছু।
যে স্লাইড চেঞ্জ বা ভিডিও কিছু দেখতে পাচ্ছি না।
So this is the connection what we have made actually. Now I will increase the switch on. First I will have to switch on the MCB. Already the MCB is on. This is the 3-phase MCB. Actually 4 points are mentioned because it is having a neutral connection also. 3 phases RYB and a neutral. So normally 4 points are there in MCB, miniature circuit breaker. So if it will be in upside, this is on. If it is in the downside, it is off. I am switching it on. You see, red color, it is written on, 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 on. So these are on. Now the supply is coming where? Supply is coming through this wire into the barrier, and this is the output terminal of the barrier. Now I am increasing the voltage. You go and show the voltmeter reading. When it will be 140, you tell me if it is 140 already. It is 140. So input voltage, this is measuring the line voltage, is 140 volt. What is our phase voltage? This is the phase voltage measuring voltmeter. How much is this? We have connected it to 300 volt range. So upper scale we will follow. It is 80. It is after that 82, 84, almost 85. So 85 volt is the corresponding, or 84 volt is the corresponding voltmeter reading. Not 84, rather we can say 83. 83 volt is the corresponding voltmeter reading. Be careful. You can see in this voltmeter or any type of such type of meter, there is a mirror. So whatever pointer is there, its image will be there in the mirror. So we should put our eye in such a position where the mirror image of this pointer and this pointer should collide. Your eye should be in that position. That time only you should take the reading. Otherwise, parallax error will be there. So let us see the wattmeter reading. Wattmeter reading is it has crossed. This is 200. So 50% will be 100. This is 50. So 50, 100, 150, 200. So 50. It is almost. We can say it is in the range of 50 only. Yes. So 50. But since our multiplying factor is 2, that means 100 watt. So reading is 100 watt. Line voltage is 140 volt. Phase voltage is 83 volt. Now let us see our corresponding A1, A2, A3 meters reading. A3 is giving the line current. It is 0.4, 0.5, 0.52, 0.54, 0.56, 0.56 ampere. This is also this is A2 ammeter. It is slightly more than this. It is, for that we will have to adjust the resistance only, nothing else.
We are just adjusting the rheostat here.
It's difficult to set all the, there is no marking on the load that this is the equal position. So it is difficult to say.
साउंड नहीं आ रहा है सर.
Because there is no sound at this moment. I am just adjusting the rheostat, okay? Because it is in a rheostat, there is not, nowhere it is mentioned 50%, 40%, 60%. Manually we will have to adjust. Even though three rheostats are identical in rating, but to find out the identical position with our naked eyes only, it is very difficult. So we need the adjustment of the rheostat also. So that is being happening here. Initially at the, to find out the midpoint is a bit difficult. That's why the adjustment sometimes become difficult. So that is the procedure which is going on, and since the adjustment is going on, so you are not able to see any voice because I am adjusting it, trying to adjust the middle point. You see nothing else.
You know, so 0.53, there will be some.
So you see, once I have adjusted, now you will be.
You can see here, if you can see the loads are, there is no marking that this is the equal position. Each are not identical specification wise, but manufacturing wise there can be some differences. So to identify exact same location for each of them, it's a bit difficult. But if we see A3 is showing us the line current and A2 is also showing us the line current, phase current. So it is almost equal. So we can say line current and phase currents are equal. Now similarly, we will vary the resistance. You see, we are increasing the, lowering the resistance. So if you see, this is another position. In that case, what we can see is that so here you can see it is 0.9 almost. This is also 0.9. A3 is 0.9, A2 is 0.9. This is slightly, A1 is slightly less, around 0.86. So why this A1 is changing slightly? Here between A2 there is ammeter additionally for this A1 additionally, but for this part there is no additional ammeter in this. So there may be some difference in the reading. But you can say if we see A2, A1 and A2 is one is showing you correspondingly A3 and A2. If we see, then one is showing you the phase current, another is showing you line current. You can see this is also in the range of 0.9, this is also in the range of 0.9. So line current and phase current relation is equal, that is established. Now we are increasing the resistance and reducing the current for the third case, so that we can reduce the corresponding current. So here you see the corresponding your currents are 0.4, 0.4, 0.4. In that case, line voltage is remaining same, 140 volt, because it will not change. Phase voltage has slightly, almost, it is supply voltage is not changing, 83 is remaining, because we are not varying the voltage, we are varying the resistance of the load, so current will change. Here, as the resistance is changing, load value is changing, so correspondingly power consumed will change. So in that case, if we see, it is in, that is in the, you can say this scale is 50, then it is around 1, 2, 3, less than fourth scale, that means less than 40, around 37, 38 we can assume. So 37, 38 if we assume, then correspondingly into 2, that means 76 watt. Previously, when we have shown 0.9 ampere current, that time also voltage was remaining same. Let us go to that position once more, because we will have to see the wattmeter reading that time also. You see, I'm changing the resistance. This part is completed now. So just a minute. Okay. So we have a small part. Can you see the video screen? Students, can you see the video part?
No, sir.
No,
Previous
sir.
video is only there.
No, sir.
No, sir.
Okay, let us wait. If it will come, it has come.
No, sir.
It's not coming.
No, sir.
Then let me reshare it once more.
Do let me do let me cock down.
Can you see it now?
Yes, sir.
Yes, sir.
Screen has
Yes,
come.
sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Okay, I'm playing it. So now you see 0.9, 0.9, it is also around 0.89. So A1 is 0.89, A2 is 0.9, A3 ammeter is reading 0.9. Voltage is remaining same, 140, and for line voltage, phase voltage, you can see is remaining same, 83. Let us see the wattmeter reading. Now we have increased the value of resistance. So in that current has increased, so the power consumed will increase for the same voltage. It has crossed 50, 60, 70, 80, 90. So it is 90 watt. 90 watt into 2. You see, each small division is 10 watt. So it has crossed, if you see carefully, it has crossed 9 small division. So 90 watt. Since the multiplying factor is 2, so it will be 180. So this is the experimental value. Then how to do the calculation, that I will explain with the annotation pen later on. For this star connection, this is the experimental procedure. So now we will make the connection for delta, then I will show you the reading and the connection, explain the connection. So my dear students, now next video, if it will appear to your screen, then I will play. Hardly we have 10-15 minutes more. Is it visible? Screen?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
सर अभी कितना है सर?
बस इतना ही, डेल्टा ही तुम्हारा बस खत्म। डेल्टा में तो ज्यादा समझाने का नहीं है। Then it will be completed. Only readings. Star portion we have completed. Now we are concentrating on the delta. Here A1, A2. This will be C2, C1. This one I have already explained during star. B2, B1. So I am directly going to the experiment. The phase current of C phase and line current entering the B and C phase joint. This I have explained in the beginning. And so if I connect it, now let us see the setup. Same setup available here. Here we have the three-phase barrier. You can see yesterday in the star connection we have used it. Same connection of the three-phase wattmeter. We are not changing it. Only these are the three loads for three phases. From previously it was connected in star. Now we have connected in delta. That's all. So what was the sequence? A1 will be connected to B2 and similarly B1 will be connected to C2 and that's all. And similarly C2 will be A. Let us see what is required. In this case A1 should be connected to C2. So A1 you see is connected to C2. A1 is connected to C2. Then what we require? Your C1 should be connected to B2. Let us see. C1 is connected to C1 should be connected to B2. Let us see. C1 will be connected through ammeter to B2. So from C1 it is going to ammeter A2. From ammeter A2 it is coming to where? B2. So C1 is connected to B2. Then B1 will go to ammeter 1. Then you can see the B1 has gone to ammeter 1. This is going to ammeter 1. From ammeter it will go to AC. From ammeter it is going to AC. That is the delta connection. This A3 ammeter should be line connected. So from L this should come to, from L you can see here, from L it should come to A3 ammeter, you see, and from there it is going to where? It will go to the joint of B2. So it is going to the junction of B2. This voltmeter is connected. This voltmeter is connected between which two terminals? Between two phases. You can see two phases between R phase and Y phase. So R phase and Y phase. So this is voltmeter. Line voltage, it is measuring phase voltage is being measured by this one. So this is connected to B2 and this is connected to B1 and B2. You see this voltmeter is connected between B1 and B2. Phase voltage, line current, phase current. Now I am switching on. So I will increase the voltage now. So you can see the line current is 0.6 ampere. This current is crossing 0.2, 0.3, 0.34 ampere. And this is also 0.3, 0.32, 0.34 ampere phase current. Now line voltage, you see 51 volt, 51 volt. This is almost also 51 volt. So phase voltage and line voltages are equal in this case. So in delta connected load, 50%. So this is 51 volt, 51 volt, line current 0.6 ampere, phase current 0.34 ampere. Now we will have to find out this ratio. We will have to find out the wattmeter reading also. Let us see the wattmeter reading. Here the wattmeter reading is very negligible. Almost it has completed only one division. One division, only small division 1. So one small division will be your 10, because you have 20 small division between 0 to 200. So one small division is 10 watt. In the previous case, we have shown you this is connected to 600 volt. 600 volt currents are in the lower setting. Lower is 2.5 ampere because these are high voltage. So according to this 2.5, 600 multiplying factor is 2. So in this case, our power will be your 10 watt into 2. That means 20 watt. Now we will change the resistance slightly and we will see what is happening. Voltage we are not changing. So in this case, we have reduced the resistance. It is 0.9, 0.92, 0.94 ampere line current. Phase current 0.4, 0.5, 52, 54, 0.54 ampere. Here also it is 0.54 ampere. So phase current in this lower resistance, phase currents are, line current is your 0.9, once more let us see, 0.94 ampere. 0.94 ampere, phase current is 0.54 ampere. 54 ampere. Line voltage, wattmeter reading, we have current has increased. So definitely the wattmeter reading has changed. It is in the range of now almost 30. Three small divisions it has covered. That means 60 watt. 60 watt. Since what is happening actually is, then deflection will be slightly more.
I'm changing, since the readings are coming very less, so I am reducing, connecting it to lower voltage rating so that deflection in the wattmeter will be more and I can take accurate reading. So instead of 600 volt, now I am connecting to 300 volt scale.
Connected to 300 volt and 2.5 ampere. So multiplying factor is 1. We are changing the resistance once more, reducing the current, changing the load positions. Point 4, then 0.5, between 0.5 and 0.52. So 0.51 ampere we can write. And phase current is your 0.3 ampere. You can see both the cases. So we will, and line current is 0.51 ampere. Voltages will remain same. You see almost same 51. Reading. Now multiplying factor is 1. Let us see. It is 3 small divisions it has covered. Calculations we require to find out the power factor and calculated power, that we will do in the class itself when we will discuss this one. This is our reading, and again you can look, you can make a broad what we can say, you can make a broad overview of your experimental setup here. So again I am telling you, these are the 3-phase loads. This is according to our present connection, this is line voltage. Here I have made this one a 3 line ammeter, these 2 phase ammeter. You can make these 2 also, any one of these you can make a line ammeter, remaining you can make phase ammeter. Just only you require the connection. This is the 3-phase wattmeter. So that's all about the experiment. Number 6, you can see E/5106, test of 3-phase star delta load connection. Now calculation is remaining left, so that we will have to see. Is it okay, my dear? Thank you very much. So we have done the video. Is there any query from the video? If not, then I will show you directly the readings once more in the tabulation sheet. Can you see the tabulation sheet? Can you see the tabulation?
Yes, sir. Yes, sir.
Yes, sir.
So readings are available. We can find out the line voltage by phase voltage ratios and the line current by phase current ratios. Similarly, you can find out, maybe here there is some difference will be there, maybe no, it's fine. Here the I line and I phase, again we are finding out the ratio. V line, V phase, we are finding out the ratio. These are the wattmeter reading for star and delta connections. Now what is the power factor? We know actually, just give me 1 minute or 2 minutes more. I know already you are exhausted, but since we know power, active power divided by voltage into current is the power factor. √3 VL IL will be your power factor. So we know what is line voltage, we know what is line current, we know what is active power. From that we can find out what is our power factor, both the cases. And what is the 3-phase load calculated? We know 3, we know V phase voltage, we know phase current, we know this power factor. We will multiply this power factor and we will see what is the measured power using this formula 3 Vp Ip cos. That's all you will have to do in this experiment. Any query about the experiment? If you don't have, then we will close for the day. Otherwise, if you have, you ask me. I will upload the videos in MS Team also. You will get it from MS Team also, and I will give you the sharing options also, editing option also. I will give it in Google
Gmail also, so that you can see from there also. PPT is already uploaded in the MS Team, so you can see the PPT from there. Any other question, my dear student? If not, then we will.
Sir, what is WYE, sir?
W?
WYE, you wrote in start delta connection alternative as first line of the experiment.
W?
YE.
Why? Star means the star connection. Actually, it is looks like Y, na? That's why it's sometimes called Y connection. Okay.
Okay, sir.
I think that's. Anything else, my dear? Otherwise, I will close for the day. In that case, you can leave now, and I will close accordingly.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Welcome.
Thank you,
Thank
sir.
you, sir.
Okay, it's all right, my dear.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome, my dear student.
तीन हजार कहाँ लगी